Hello sir, my name is Aditya Pratap Singh and today I am going to talk about the virtual memory management in Mac operating system. So the one question that comes to our mind is that why the virtual memory management is really important. So efficient memory management is an important aspect of writing high performance code in both operating system X and iOS. Minimizing and the memory usage not only decrease our application memory footprint, it also reduces the amount of the CPU time it consumes. Both OS X, or should I say Mac operating system, and iOS include a fully integrated virtual memory system that never turns off. It is already on. Both systems also provide up to 4 gigabytes of the addressable space per 32-bit process. In addition, the OS X provides the approximately 18 exabytes of the addressable space of the 64-bit processes. Even for the computers that have 4 or more gigabytes of the RAM available, the system rarely dedicates this much RAM to a single. So to give the processes access to their entire 4 gigabytes or 18 exabytes address space, OS X uses the hard disk to hold the data that is not currently in use. As memory gets the full section of the memory that are not being used are returned to disk to make the room for data that is needed now. The portion of the disk that stores the unused data is known as the backing store because it provides the backup storage for main memory. Unlike the Unix-based operating system, OS X does not use the pre-allocated disk partition for backing store. Instead, it uses all of the available space on machine's boot partition. So as we have discussed the importance of the memory management in the operating system, now we are going to talk about the virtual memory, which is a really important aspect of the memory management. Virtual memory allows an operating system to escape the limitations of the physical RAM. The virtual memory manager creates a logical address space for each process and divides it up into the uniformly sized chunk of the memory called pages. The process and its memory management unit maintain a page table to map pages in the program's logical address space to the hardware address in the computer's RAM. So as we are discussing about the pages, there is an important term that comes, the page fault. So what is the page fault? If an application accesses an address on a memory page that is not currently in the physical RAM, then it causes the page fault. When that happens, the virtual memory system invokes a special page fault handler to respond to the fault immediately. The page fault handler stops the currently executing code and locates a free page of the physical memory and loads the page containing the needed data from the disk and updates the page table and then returns the control to the programmer's code, which can then access the memory address normally, and this process is known as paging. So the another question that comes is that if there are no free pages available in the physical memory, then what happens? Then the handler must first release an existing page to make the room for the new page. And how the system release the pages depends on the platform. In the Mac operating system, the virtual memory system often writes the pages to the backing store. The backing store is a disk-based repository containing a copy of the memory pages used by a given process. Moving data from a physical memory to the backing store is called the paging out or swapping out. Moving data from the backing store back into the physical memory is called paging in or swapping in. In iOS, there is no backing store, so the pages are never paged out to the disk, but the read-only pages are still paged in from disk as needed. So, in the Mac operating system and the earlier versions of the iOS, the size of the page is 4 kilobytes. In later versions of the iOS, A7 and A8 based system expose the 16 kilobyte pages to the 64-bit user space backed by the 4 kilobyte physical pages, while A9 system exposes the 16 kilobyte pages backed by the 16 kilobyte physical pages. These sizes determine how many kilobytes the system reads from the disk when a page fault occurs. The disk thrashing can occur when the system spends a disappropriate amount of the time handling the page faults and the reading and the writing pages rather than executing the code for a program. So now we are going to talk about the virtual memory system in the details. The logical address space of a process consists of a mapped region of the memory, and each mapped memory region contains a known number of the virtual memory pages. Each region has a specific attributes controlling such things as inheritance. Portion of the region may be mapped from a parent region, write protection, and whether it is wired. Wired means it cannot be paged out because the region contains a known number of the pages. They are page aligned, meaning the starting address of a region is also the starting address of a page, and the ending address also defines the ending of the page. So then there is an also term known as the kernel. So what is an kernel? The kernel associates a virtual memory object with the each region of the logical address space. The kernel uses a virtual memory object to track and manage the resident and the non-resident pages of the associate regions. A region can map to a part of the backing store or to a memory mapped file in the file system. Each virtual memory object contains a map that associates the regions with either the default pager or the vnode pager. The default pager is a system manager that manages the non-resident virtual memory pages in the backing store and the fetches those pages when requested. The vnode pager implements the memory mapped file access. The vnode pager uses the paging mechanism to provide a window directory into the file, and this mechanism lets us read and write the portion of the file as if they are located in the memory. So in addition to the mapping regions to either the default or the vnode pager, a virtual memory object may also map the regions to another virtual memory object. The kernel uses this self-referencing technique to implement copy on write regions. Copy on write regions allows the different processes to share a page as long as none of them write to that page. When a process attempts to write to the page, a copy of the page is created in the logical address space of the process doing the writing. From the point forward, the writing process maintains its own separate copy of the pages when it can write to any time. Copy on write regions let the system share large quantities of the data efficiently in memory while still letting the processes manipulate those pages directly if needed. These type of the regions are most commonly used for data pages loaded for system frameworks. So as we have talked about the virtual memory, there is a wired memory. Wired memory stores the kernel code and the data structures that must never be paged out to the disk. Application frameworks and the other user level software cannot allocate the wired memory. However, they can affect how much wired memory exists at any time. For memory, an application that creates the threads and the ports implicitly allocates wired memory for the required kernel resource that are associates with them. As you can see, every thread, process, and the library contribute to the resident footprint of the system. In addition to your application using the wired memory, however, the kernel itself requires the wired memory for the following entities: virtual memory objects, the virtual memory buffer cache, input-output buffer caches, and the drivers. Wired data structures are also associated with the physical page and the map tables used to store the virtual memory mapping information. Both of these entities scale with the amount of the available physical memory. Consequently, When you add the memory to a system, the amount of the wired memory increase even if the nothing else changes. When a computer is the first booted into the Finder with no other application running, wired memory can consume approximately 14 megabytes of 64 megabyte system and the 17 megabytes of 120 megabyte system. Wired memory pages are not immediately moved back to the free list when they become invalid. Instead, they are garbage collected when the free page counts falls below the threshold that trigger the page out events. So here comes the question about the page listing in the kernel. The kernel maintains and queries three system-wide lists of the physical memory pages. The active list contains the pages that are currently mapped into the memory and have been recently accessed. The inactive list contains the pages that are currently resident in the physical memory but have not been accessed recently, and these pages contains the valid data but may be removed from the memory at any time. The free list contains the pages of the physical memory that are not associated with any address of the virtual memory object. These pages are available for the immediate use by any process that needs them. So when the number of the pages on the free list below falls below a threshold, the pager attempts to balance the queues. It does this by pulling pages from the inactive list. If a page has been accessed recently, it is reactivated and placed on the end of the active list. In the Mac operating system, if an inactive page contains the data that has not been written to the baking store recently, it contains must be passed out to the disk before it can be placed on the free list. In iOS, modified but the inactive pages must remain in memory and be cleaned up by the application that owns them. If an inactive page has not been modified and is not permanently wired, it is stolen and added to the free list. Once the free list size exceeds the target threshold, the pager rests. Now we are going to talk about paging out process. In Mac operating system, when the number of the pages in the list dips below a computed threshold, the kernel reclaims the physical pages for the free list by swapping inactive pages out of the memory. To do this, the kernel iterates all resident pages in the inactive and active lists, performing the following step. If a page in the active list is not recently touched, it is moved to the inactive list. If a page in the inactive list is not recently touched, the kernel finds the page's virtual memory object. If the virtual memory object has never been touched before, the kernel pulls an initialization routine that creates and assigns a default pager object. A virtual memory object's default pager attempts to write the page out to the baking store. If the pager succeeds, the kernel frees the physical memory occupied by the page and moves the page from the inactive to the free. Now there is paging in process. The final phase of the virtual memory management moves page into the physical memory, either from the baking store or from the file containing the page data. A memory access fault initiates the paging process. A memory access fault occurs when code tries to access the data at virtual address that is not being mapped to the physical memory. And there are the two kinds of the fault. A soft fault occurs when the page of the referenced address is the resident in the physical memory but is currently not mapped into the physical space of this process. A hard fault occurs when the page of the referenced address is not in the physical memory but is swept out of the breaking process or is available from a mapped file, and this is what is typically known as a page fault.